I'm Clayton Turner. My background is in processing biomass into all sorts of stuff. I've been a professor of distilling here locally at SPSCC for distilling engineering. We qualified in the top 284 teams of the X Prize, beating out a couple thousand schools for the $100 million X Prize qualification. So we realized that we should probably switch from hemp over to wood as our initial process material. And the reason for that being is there's so much more of it. Last year, unfortunately, we only grow 19,000 acres of hemp. And when you're talking about putting in a facility that's gonna do 180 tons per day per line when we scale up from these machines, that's a lot of biomass and a lot of material we need to eat. Luckily, I was born in Skagit Valley and I realized, wait a minute, I live where wood lives. Like, I'm where it comes from for the whole country. The softwood production for non-pelletized wood pretty much happens here. So why don't we just leverage what we have and also help take care of forest fires? So when we get our materials, as you've seen, it breaks down into a carbon material, and then it goes also into a tar material, a wood vinegar material, and then we get a gas material that we actually use in our process. We run that machine for an hour, hour and a half with propane, but then after that, its own heating process creates a cycle with the logs where their own gas keeps heating themselves, and we're able to really efficiently get our material to carbonize. And it turns into carbon like this right here. So when we have carbon like this right here, to get it to a usable state, we have to micronize it or potentially dope it or add other materials to it or nano coat it to get it to go into a bunch of different stuff. And that's really where our background comes in of chemistry and our biochemist, Steve Lund, and his background. And coatings, emulsions, things like that is really what we've been doing for years, as well as milling down products and finding a use for their waste. So when we start looking at the products, we've got things like biochar. You'll normally hear biochar as the thing that people make when they carbonize wood through pyrolysis. But biochar is only a $44 million industry. And what they do is they pretty much just dump this in the ground. When you do that, you generate carbon credits, which is cool. But we thought, can't we do something better? Could we maybe do a different industrial process? So it turns out when you micronize biochar, you can go into drip lines. And that actually means that the material will soak into the earth, and it does penetrate down like 4 inches at least into the ground with this carbon. When you do that in sandy or loamy soil, like down in California, you can increase water retention of the soil by 80%. You're adding characins to the soil, which stimulate plant growth. Like after a forest fire, they say the forest grows back up. Well, it does that in part by the characins, which is really concentrated in our wood vinegar. And so with these processes, you are able to sequester carbon. So drip line material sells for up to $99 for a 5-gallon bucket. And it's used in things like hemp cultivation, hydroponics, all sorts of stuff. It's really useful material to have. But then we thought, there's other uses too. So we started micronizing that material even further. This material over here that I have in my hand is smaller than 10 micron. And we've gotten down in-house with our own milling down to 5.77 micron. To give you an idea, a blood cell is only 5 microns across. So we're getting down to the size of a single blood cell or double the size of a blood cell. And when you have a really tiny material like that, it starts to get really strong and it starts to get really big surface area. And it starts to bond to things and give them those properties of hydrophobia, of thermal resistance, because this has already been up to 550 degrees and off-gassed everything in it, and it gives it strength. One of the neat things about what it does with strength is the strongest substance that we've been able to make as man was graphene. As most people here have heard of graphene before, I'm sure. As of February, it is no longer the strongest material between it and borafine. Turns out this stuff right here in this bag just blew it away. Atomic layer amorphous carbon is actually 8 times stronger than graphene according to tests out of many universities. That's very exciting for us because when you think about Washington, you think about aerospace, you think about the technology and the manufacturing we're doing, if the resins, if the polymers, if the carbon fibers in the hood of your car can be made thinner and stronger and better and more heat resistant, and they don't degrade with UV or oxidation, that's going to change our industry of how we operate. And I might mention that most carbon black materials and amorphous carbon materials, about 70% of them are made in Russia, China, and India currently. And you can think about what the tariff situation is doing there, what Buy American is doing there, and how that's impacting us. So these micronized carbons can be doped with different materials that we've found, and we're working with battery manufacturers to actually improve their process and make their batteries smaller, stronger, and more efficient, because we can dope the carbon itself with these materials, which gives it massive surface area. If you take a teaspoon of that 10 micron material, it has the same surface area as a football field. You can think about how our brain works the way it does because of all the folds and connections in it. Micronized carbon works in a similar way. All that surface area lends to being able to coat it with materials, dope it with materials, and get better reactivity when you put it into an environment where it can make contact with an aqueous fluid. So that's a lot of the carbon, and I'll delve more into that in a minute, but I don't want to overstate the use of our wood vinegar, which has carotenoids in it that help plants grow and all these other things. But the other thing it has is acetic acid. And what's great about that is acetic acid is a precursor for calcium acetate, which is used in farming, high value item, and also potassium acetate. Why am I excited about potassium acetate? Potassium acetate is the key to the potassium ion battery. And if you can make a potassium ion battery, they think that it's gonna pretty much be competing with lithium ion pretty quickly. It's having a lot of great results. And why is that exciting? Well, the research for it is done at the UW and OSU. So we're in the perfect place of the home of the potassium ion battery, and we can make it, its anodes, its cathodes, the plastic around the container of the battery, all of that can be made from our carbon, at least in some amount of 30% or more. So it's really exciting to have that potential to turn what is our lumber industry into the new high-tech materials industry. And that's before we get into things like our cement products and asphalt. Another thing I'd have you do is check out the weight difference, which we just weighed it. It's about 50% difference between the first block, which has 1% in it, or none? Yeah, first block is 1%, so it's actually lighter than regular cement too. And the last block is what percent? It's 20%. So it's 20%. By adding 20% carbon to our material, it made it 50% lighter. So this is actually, because of the volume of the material, this block at the end, you can feel it, is half as heavy as the first block with 1%, which is still lighter than regular cement. So when you get a chance, walk up and grab the first block, grab the second block, see it for yourself. It's a big difference. Now, these aren't fully cured yet. We haven't even been 28 days. The 20% carbon, yeah, they're not anywhere near 28. Yeah, no, so these are fresh. This is fresh cement, by the way. When you're touching it and you're holding it, understand that's fresh cement. Another thing we've got over here in the cement category is this little block right here, which is actually, when you touch it, it might be a little brittle, it might be a little different. That's because this one has a whole bunch of calcium carbonate in it and some other great things that we put in it, which actually helps cement self-heal. So that's an experimented self-healing carbon. But you can come over to these are much more durable. These are more of our just traditional adding carbon to the mix. The other thing you can do, you can add it to drywall. The Gypsum Council, if you look up on the Gypsum Council of the USA, they say they make about 1 billion square feet of gypsum-based drywall per year. That drywall would sure like to be hydrophobic because of all the flooding across the country, so that it sheds water, so that it doesn't hold mold, so it shoves that out better. Also, in the case of a fire, what's nice about our material, we've already cooked it up to 550 degrees, so it's not gonna off-gas. You think about a fire and a house heating up and all those vapors that build up, our material's already been heated up really hot, so it's not gonna off-gas like a biomaterial. The other great thing about that is it doesn't really raise the cost to add our carbon to that material very much. If we just had the price of the basic material, it'd be the same. And each of these additives don't need to be special processed when they're putting it in. You don't need new machinery as a plastic plant to make our plastic and put 30% of our carbon into plastic. You don't need to change your line for drywall production. You don't need to change how you make asphalt. You don't need any special machines, bricks, blocks, whatever to make our cement. You take our magic dust, you pour it into the product, you get a better performing product, and you sequester carbon when doing it. So isn't that better than just throwing all this material underground? So That's generally our big stack of stuff, but I want to end with one more thing. We're actually using sound waves right now to micronize the carbon down to a nanometer scale. So we're running tests right now even to micronize this material. And we have another partner based out of Tacoma that is actually looking at the one product that we have that's a waste material, which is some carbon dioxide. Now mind you, we sequester more than we emit. We actually qualify for carbon credits, but they want to take our CO2 from our green recycled source and they want to make nanotubes out of it. And they're making nanotubes right now out of our exhaust gas. And what's exciting about our system is we get a lot hotter than other systems. At full operation right now, we're at 550 C coming out the tube. At our bigger systems, we'll be up over 700 C. The systems that like this, that use catalysts, they operate at that temperature range. So our exhaust gas doesn't need any extra energy to be heated up to be compliant with what they're doing, and it comes from an already recycled source. That's carbon nanotubes in production as well, and we're about to run a pilot with them where they come snap their unit to our unit and we make some bio-based carbon nanotubes. So that's currently where the future is and where we're heading, but today we're in cement, tomorrow we're in plastic, the day after, the future in space.